Okay, one application I left off because we have done quite a bit with second order equations with constant coefficients, right? That's like y double prime plus by prime plus cy, right? Equals 0. This is a homogeneous case. We're using R here. AE to the RT, or AE to the lambda t, but I'll say AE to the RT because I think that's a notation we're more used to. Shouldn't matter because we've used lambda also. Okay. Right.
Oh, yeah.
Maybe you can factor it, but if not, you got this, right? And also, you might need this if this comes out negative. Then when you plug it in, you're going to have an AE to some number plus some imaginary number, right, times 2. And you got to know how to deal with that, okay? And we've done the 2 simple cases, okay, where you have 2 solutions that are different. Okay, we have not dealt with the case where you have repeated real solutions. Okay, in other words, where this discriminant is 0, because that involves reduction of order, and that's hard.
Okay.
Not hard. It's more hard
Okay.
than what we're doing. Okay. It goes a little deeper. It goes to some technique, and that's one of the first things we're going to do next week.
Awesome. Looking forward to that.
Okay. And a couple of other things, and then we'll have this whole thing done. Okay. And the so you got to know how to do that. You're doing that just great. It's been over a month. Okay. So you want to review that, but it's easy because it's really easy to recognize when we have second derivatives. Okay. And the premise is easy. Okay. Then if it's non-homogeneous, it's still constant coefficients. I'm not sure what they use here, so we'll just use Q of T, but I think they might use G in your text. Again, I seldom look at the thing, okay? Because what you don't need me to do is just repeat things the way you see them in the text. You need to see it the way I explain it. You need to see it the way the book explains it. Take your choice of which one you really want to look at.
Okay.
Okay? But when you have 2 different ways of explaining the same thing and seeing the same thing, a lot of times they're exactly the same. But when you have it from 2 different perspectives, if you work it out, you learn it better. Okay? So I don't look at the text much. Because then if I do, I'll start doing it the way the text does. Either that or I just have to go rewrite the text and do it right. And I'm joking because it's a great text. Okay, so when you have this, you gotta use trial solutions. Okay? For example, if Q of T has a sine or cosine in it, then your trial solution is gonna have sine or cosine. Okay? So for example, the C1 sine of T or plus a C2 cosine of T, and that should jog your memory as to how that works. Okay? Then you just plug that in. See how the derivatives work out. The coefficients of the sine have to equal whatever the coefficients of the sine is here, and coefficients of the cosine have to match the coefficients of the cosine. Okay? And of course, if it's a polynomial, okay, then it might be like an AT squared plus BT plus C, where you put the degree here, depends on the degree here, with a little common sense. Okay? Okay, so now I can start talking about applications, because some of the applications in chapter 3 just lead right into the applications in chapter 4. Okay? So, for example, in chapter 4 we talk about oscillatory motion, where in chapter 3 we just talk about motion along in one direction. Okay? The equations are always straightforward to solve. Maybe not quite all that straightforward. Okay? Sometimes they get a little involved. But if you understand Newton's second law, you haven't had physics, so you don't really understand Newton's second law. If you just believe it,
Okay.
the net force is equal to mass times acceleration. Acceleration is the second derivative of position. Okay?
Okay.
Then you get the equations. There are a couple of tricks, but that's what you've got. Okay? So let's see how that works out.